2, 1, 2. Okay, welcome back after our coffee break. You still, if you had a chance to scan and get us a feedback, you will have that chance to maybe do it again in the end. Maybe before we will start, and I will give the voice to Bobby. Once again, I'm reminding that we have some nice t-shirt, maybe not run right now, but there will be definitely a time after. The SONiC t-shirts are really limited. Even I don't have my one yet, and hopefully one will stay or will left, yeah. So,
perfect.
Stage is yours.
Thank you very much. Hi everyone, my name is Bobby McGonigle. I'm a software engineer at Nexthop AI in the Layer 1 team. Today my talk is on configuring and debugging the physical layer in SONiC. So that's everything from ASIC SerDes and optics through to the CLIs that you'll actually use when you have a link issue. There's some theory that we'll need to go through, but I'm not going to go through stuff like the L1 sublayers. It's going to keep it just kind of to the bare minimum that's needed to understand the debug outputs that SONiC has. We'll look a little bit at what's changed in L1 and what's been added to SONiC in the last year. So adding all that together into some form of repeatable debug workflows. So why does layer 1 matter now, in this AI world? Well, every packet, every sensor, every tensor rides on layer 1. So for AI training, that means GPU to GPU, fabric latency and loss directly hit time to train. Bursts and marginal links are tail latency killers. Tail latency being the measurement of the delay experienced by the slowest packets. So if L1 is broken, nothing else works, and that's where AI is different. It has desynchronization points that are tightly coupled to GPU utilization. So tail latency almost directly translates into worse job completion time and GPU burn. In a general cloud or enterprise, the same tail effects do exist, but they might be spread across independent user requests rather than a single global training step. When we're talking about layer 1 in SONiC, I'm talking about pretty much everything from the ASIC's internal SerDes out to the cable or the fiber. So that's the electrical lanes, that's FEC, that's modulation, that's transceiver control and the path that programs them in SONiC. Really getting L1 right means that all of these different hardware pieces use the exact same configuration and the hardware state actually correctly reflects that. So SONiC's kind of L1 origins are obviously kind of baked into hyperscale, and it did all kind of just work, with a couple caveats. One being that you were using these kind of fixed static configurations, you'd load them onto the device and you wouldn't really change them. You were generally using kind of copper DACs at lower speeds, which were kind of forgiving, and you weren't using optics with DSPs or using any kind of breakout configurations. Once the configuration was there, you weren't doing anything dynamic really at runtime, no CLI, no speed change, those kind of things. And it all kind of worked happily as long as you didn't go too far off the beaten path. So I talked about, the internal PHY SerDes and, something like having an external PHY where there's another PHY chip sitting in between the internal ASIC and the front panel. That can be there for a couple different reasons, like, if there's too much trace loss, you might need to retime the signal. You might want to convert X number of lanes to Y number of lanes in the front panel. There's a few different reasons, but it just adds another configuration parameter, and those type of things diverting off the happy path just didn't really play well with kind of SONiC's early origins. So it did have some quirks, and they were all kind of generally fine as long as you knew its limits. So breakout limitations, when I'm talking about breakouts, I mean you have, say, an 800G front panel port, and you logically split that up into sub-interfaces. So, an 800G port can be broken up into 2 by 400G or 8 by 100G, for example. To actually get these front panel port configurations, you have the concept of a hardware SKU and a hardware SKU profile. So these are kind of, fixed front panel port configurations, and you have to change them and request a new hardware SKU from a vendor when you want a different front panel port layout. And generally, that could take some time, or you could try to come up with your own, but if you don't know much about the hardware underneath, it's kind of tough to do that. From an operator's point of view, it was somewhat inconsistent. So, interface ranges is a good example. Some supported interface ranges, some don't. So you kind of have this like consistency across the device. And it also lacks some of the essential commands that you'd need. So changing hardware SKU, maybe inspecting transceivers, maybe trying to take a look at SerDes statistics. It was just somewhat easy in the beginning to drift from the happy path. A couple of pain points, some awkward workflows, but it assumed, a basic simple L1 world, which is completely fair because it was, but like everything, hardware moved on. Which brings us kind of to today, where the environment's not too different, but this might be somewhat familiar for people who've worked on SONiC. You have a config DB with your desired configuration, it gets pushed into appdb, and a side call will happen. syncd will program your internal ASIC PHY, and then concurrently you'll have PMON kicking off a transceiver daemon, which will take that same config from config DB and hopefully program the transceiver. So the end goal is hopefully these two things are programmed correctly and you end up with a stable link that's operationally up. So this is just to remind us that the physical world is pretty hostile when you get to these new speeds. You're fighting against loss on the path, reflections from every bad impedance transitions, crosstalk between lanes, interference, etc. Which was completely fine at lower speeds, 10G. You could get away with this kind of stuff, but once you get to these 100G, 200G per lane, the physical world is just going to call your bluff, and it's not very forgiving. So what has changed? It's not really that just the links have gotten faster. The whole stack has evolved. So we've switched modulations from NRZ to PAM4. Lane rates have increased. We've started relying pretty heavily on optics with DSPs, FEC inside modules, more complex management and monitoring of transceivers using CMIS. So L1 today is really just a combination of smarter transceivers, more capable SerDes, different modulation, and a heavier reliance on FEC to make those links viable. So when you're debugging, you really need to know what form factor you're dealing with, and these are kind of some of the common ones you might see in current switches. So you have an SFP 1 lane, QSFP 4 lanes, QSFP-DD 8 lanes. You might have the same faceplate that has QSFP as well as QSFP-DD. So knowing that which one is which is pretty important for knowing the capabilities of this one has 4 lanes, this one has 8 lanes. They might not be capable of the same speeds. Under the hood, pretty much every single port has these SerDes blocks. They're serializer, deserializers, and they turn parallel data inside the ASIC into serial signals on each lane. Really, they define the capabilities of a device. So instead of thinking, I have a 102.4 terabit per second switch, from an L1 point of view, you're really saying, I have 64 ports of 1.6T. Each of those are capable of 200G per lane. So really, every port problem kind of starts with a per lane SerDes problem first, from the L1 point of view. So once we understand that, SerDes are just an RX and a TX pair, there's 2 ways that we can make it faster. We can increase the speed of the lane, add more lanes. And with different generations, we've done that along the way, or a combination of the two. But these SerDes just aren't static. There's a bunch of different configuration knobs that are important, and we have things like Autonegotiation, where you have 2 peers, they advertise their capabilities, and they'll come to some form of an agreement on those settings. And then we have stuff like link training, where the transmitter will figure out the proper equalization taps, coefficients of a small FIR filter, and they pre-distort the waveform to kind of counteract and cancel the channel's loss, somewhat similar to stuff like noise-canceling headphones. Which brings us to modulation. There's 2 different types. In the past for lower speeds, we had NRZ, fairly simple, high is equal to 1, low is equal to 0. It was well understood, it worked well, 10G, 25G. And then we got the PAM4. So this is used at 50G, 100G, 200G per lane. This is kind of you're now getting into the high speed. It has 4 signal levels instead of 2, so 0, 0, 0, 1, 1, 0, 1, 1. Obviously, we can now encode 2 bits per symbol, which is great. We double the throughput without doubling the signaling rate, but it brings some challenges. So obviously, it packs in more data, but the signal levels are 3x closer. So trying to differentiate between them, there's a lot less room for noise, which is why sometimes we have cables that work perfectly fine at NRZ speeds, but when you bump them to 50G per lane, you start seeing some issues. It's also why FEC went from nice to have to absolutely required, and it is required by 802.3 spec for any speeds 100G and greater. So FEC, or forward error correction, it's this transmitter adds redundancy bits to every block of data called a codeword, and I'll talk about codewords a little bit and what comprises a codeword and a symbol in the next slide, but the receiver uses that redundancy to detect and correct any errors without retransmission. So in some ways it's similar to a checksum, except it can actually fix the data. the maths behind it is pretty complex, so I'm not going to get into it, just the bare minimum of what's needed to understand FEC histogram, Pre-FEC BER, and all those kind of debug tools that you'll need. You'll see a couple different types in SONiC, but 99% of the time you're just going to see RS FEC from now, but at lower speeds like 10G, there is Firecode FEC as well as no FEC as a viable configuration in SONiC. So the important point really with FEC is that there is a hard limit. Each FEC symbol is 10 bits. A code word is either 528 or 544 of these symbols, including parity symbols. So for lower speeds, 10G, 25G at that NRZ modulation, we can correct up to 7 errors. And at faster speeds, we can correct up to 15. So this corresponds exactly with FEC histograms, if you've seen the debug output for those. Bin 0 is 0 symbols needed to be corrected, whereas 15 is 15 symbols needed to be corrected. Anything after 15, FEC couldn't do its job, and you'll get uncorrectable code words and ultimately a link flap. So in terms of actually debugging layer 1, we have a mental model now of the physics and the hardware and what's actually changed, but the rest of the talk is going to be about how to actually debug now in SONiC. So what's been added in the last year, commands you'll lean on, and how to essentially interpret the results so that you can decide for yourself, do you want to reseat, reconfigure, or replace a module? Yeah, so I just want to take a little second to pause on just what's actually landed in the last year. So if you were to take this and compare it to previous years, the numbers would be significantly less. Like the number of contributions from multiple different vendors and companies at the moment is significantly more than it was in the past. So the community is thriving in that regard and constantly improving the L1 area. Obviously, there's still work to be done, but it's on definitely an upward trajectory. So as someone debugging a link issue, what do you need to know? So really, there's a couple of things you absolutely need to know about, and SONiC needs to provide. You need to be able to check link state, so you need to be able to check speed, FEC, all these different configuration parameters for the SerDes, as well as transceiver. Transceiver presence, being able to inspect whether or not the optic you're using is correct for this type of requirement, whether that's speed or some other configuration. And then you also need to be able to inspect the transceiver itself, so data path state, being able to see is the ASIC talking to the module, being able to see is there light coming into the module, CDR lock, alarms, whether that's power or voltage. Show interface status, so this is pretty basic. This has been around for a long time. It gives you a snapshot of the operational status. We can see left to right. We can see the SerDes lanes being used. We can see that it's operationally up, admin up. This is great as a starting point, but a link could be flapping and you don't realize just because the time you actually ran this command, it so happened to be up. Which kind of brings you to, if the show interface status commands look weird, this is generally when you'll go to dump state port, and it kind of works as like a truth serum command. It'll dump all the information from config DB, application DB, as well as ASIC DB for a port, and you can kind of cross-reference the three. So you can check that the configuration that you thought you were applying actually did get applied as well in both the ASIC and in AppDB. And if you look in all this information and they all agree between the three databases and the link is still misbehaving, then you can pretty confidently move on to the physical aspects and start debugging the physical side. Which brings me to L1 summary. So this is more kind of like show interface status and what it should be for layer 1 specifically. We can see not just that the link is operationally up or admin up, we can see if it's flapped, we can see when it was last up, we can see the transceiver, the part number, and the vendor itself. So all of these kind of things that you want to see as a general snapshot before deep debugging to check whether or not all your links are healthy, and you can make some correlations to spot six ports pretty quickly in a big system here. So, you might be able to correlate all of the vendor X transceivers are having link flaps, maybe some other issue with vendor Y, those type of things. And it gives you an opportunity to, at a high level, see what's going on. Which then brings me to FEC counters. So starting from left to right, this is kind of how you're going to measure generally what's the health of my link. So you'll see FEC corrected code words on the left, absolutely normal at PAM4 speeds. The FEC engine is doing its job. You're going to see those incrementing. Where you don't want to see is any FEC uncorrected code words, which is the second from the left. So if you see anything there, that means that there was more than 15 symbol errors in your FEC output, and FEC wasn't able to correct it, and you've got a link flap. One that's used pretty extensively to like measure the link quality is the Pre-FEC BER. So we can see here it's e to the minus 11, e to the minus 9, e to the minus 10. You know, generally we want to see that being e to the minus 11 or e to the minus 12, but you know, that's just not the nature. Maybe media settings, those TXFIR filters aren't applied. You know, this is your measure of how well is the SerDes able to actually, how well is FEC able to do its job. So looking a little closer at that, we have the FEC histogram output. So on the left, this is, you know, I think this link was e to the minus 9 from the previous snapshot. We see FEC bins 2 and 3 incrementing, which we don't really want to see. In an ideal world, it'd be 0 and 1, but 2 and 3 is okay. FEC is still doing its job. It's able to get to 15, but realistically, if you want to have these links in operation for a long time, they can't be incrementing. Snapshot on the right is actually a link that when you looked at show interface status was operationally up, but behind the scenes it was flapping pretty consistently. So we can see that all the FEC bins were completely incrementing. Bin 15 incrementing, so obviously bin 16 was incrementing too, which meant that we were getting link flaps. So then to check the link flaps, we go back to show interface flap or show interface L1 summary again like before, which shows, you know, okay, this link actually was flapping 91 times, which makes sense when we go back and look at the fact that the FEC histograms were pretty bad. So show interface transceiver is how you're going to interrogate the module itself in terms of, you're going to look at the application advertisements. Does it say it can support 1.6T when I'm trying to set 1.6T on the port? It's going to tell you what application is currently loaded. It's going to tell you the part number, the vendor, etc. How many lanes, the power class, and so on. So you're going to use this pretty much to confirm that you're using the right optic or module for the job. Transceiver status kind of concentrates on live CMIS state and alarms. CMIS is the common management interface spec that's been introduced from OSFP and QSFP-DD kind of generation of 8-lane speeds. It's pretty good. You'll be able to see, you know, was there any failed transitions? You'll be able to see the data path. You'll be able to see the configuration. You'll be able to see, is there any alarms, whether that's loss of light or maybe temperature or so on. So this is kind of really a good way to tell whether or not your module is in a healthy state. Things you don't see in terms of improvements. There's a lot happening pretty much under the covers that, you know, hopefully as a user you don't really have to think about. So there's been some configuration and initialization sequencing changes that, you know, respect maybe CMIS timing quirks and some module specific behavior. So there's retry and debouncing logic. So hopefully that keeps what are or can be transient blips in configuration from turning into kind of permanent faults, whereas they may have in the past. Another example is a lot of the debuggability stuff that's going on, increasing the amount of timestamps that are in the outputs, new CLIs, etc. So looking forward, there's a deeper push for SerDes-Side visibility. There's been a bit of a shift where, you know, it's great that we have these transceiver debug outputs and we can take a look at the module, but a lot of that information comes from the digital signal processor that's on these optics. And a lot of the emerging technologies right now are getting away with the DSP from these modules and pretty much putting all of the work of cleaning up the signal on both the TX and the RX path on the SerDes now that they're more capable. So having that SerDes statistics and being able to look at what's going on in the SerDes is incredibly important for what's going on and what's coming in the future. And then as well as, you know, supporting these new technologies like CPO, LPO, LRO, and then other diagnostic tools. So in terms of a call to action, there's a few things here really, you know, engage with the community on GitHub, the same as other people have said before, you know, join the L1 subgroup, work group meetings, you know, contribute code and documentation. A big one is testing in the L1 area. There's only 2 tests right now that exist upstream. And, you know, that's obviously, you know, there's different testing in other ways, but that's one area that could definitely improve if there was a call to action. So I guess I'll kind of start ending with how the L1 story is no longer really experimental in SONiC. You know, there is enough there to be able to debug these links. So there's a data-driven config path. You know, we have tools like FEC histogram, CMIS state dumps, you know, Pre-FEC BER, being able to read the DOM and all the stuff from the DSP on the transceivers. So we do run this in real production today with, operators can decide reseat, reconfigure, replace modules on clear signals from these commands. And in terms of closing the gaps with traditional network operating systems, there's obviously some areas where SONiC is still weaker today. Many of the CLIs are kind of expert CLIs where you really need to know what you're looking for, and there's no single pane dashboards or easy ways to for someone not very familiar with L1 to, take a look and figure out what's going on. Again, the community test that I talked about before is another area. And again, general operational polish, so event correlation, alerts, RCA flows are a little less turnkey. But we are doing stuff about it in the L1 subgroup. We're standardizing CLIs, so timestamps and increased debuggability across platforms, and hardening transceiver and lit sequences and fault recovery. So the goal really is to make SONiC L1 as easy to operate as a traditional network operating system, and hopefully more transparent than any of them. Thank you. That's it. Any questions? Yeah.
Hello, David Roy from HP. Is there any ongoing or work in progress for exposing coherent optic KPIs like OSNR or stuff like that?
Yeah, that's pretty much already existent today.
Okay.
Yeah, there's some of the work that's gone on recently for 400G ZR and 800G ZR. There's debuggability for those modules.
Okay, thanks.
Yeah.
Anyone else? Any extra question? So maybe I have one, if I can.
Of course.
Speaking about the cables, I know how tricky that is, especially copper, when we are going to those extremely high speeds. So what is your experience? I am not talking about all the details, but there is a couple of vendors, obviously. But let's say going with such as 800G, what you saw on your all tests, like a maximum, let's say, reasonable stable length on, for example, such as DACs, yeah? And then going to 1.6, it is new for almost all of us, yeah?
Yeah, generally we've seen, especially with the bridge from 800 to 1.6, is that DACs just don't have a good enough BER. Essentially the actual signal needs to be retimed, so whether that's an AEC or switching to AOCs or optics, then that's kind of what's happened. Yeah, generally the performance of DACs at these higher speeds is just not good enough.
Okay. How about then 400G? That's
completely fine, yeah. And 800G is fine in many cases. Yeah.
Thank you. Thank you. Applause.
Thank you.